Hello, everybody. Thank you for joining us for our, I think, third team pitch this week. Today, we are hearing from the team called Gun Detection. Hopefully, they'll have a better name soon. Team members are Jimmy Chen, Daniel Deng, Akash Singh, and Jiho Ro. As always, if you have any questions for us or for the team, please feel free to message the appropriate person on Slack. And go ahead and take it away, guys.
Okay, sounds good. Let me share my screen real quick. All right, can everyone see the slides?
Yee.
Okay, sounds good. Sounds good. So our project is gun detection. So basically, the context for this is, with the prevalence of like a lot of mass shootings in the U.S., we wanted to basically create a system where we could use pre-existing like cameras to detect guns with like a high degree of accuracy and in real time. So basically, with this focus, right? We chose to first start out using an algorithm called YOLO v4, which is a single shot detector. And basically with this, we can process with relatively affordable hardware in real time guns from like video streams. So in our first attempt, we tried training the model with just 2,700 images of guns that have all been labeled with basically bounding boxes of guns. And we achieved pretty decent results. As you can see in the chart, we achieved a max mean average precision of 88.7%. For a bit of context, what mean average precision means is basically in the test data set, we have a bunch of images, and each image that has a gun has bounding box around the gun. And basically, when we run it through our algorithm, we determine another box that the algorithm thinks that there's a gun inside. And the mean average precision is basically on average, how much overlap is there between the labeled box and the box that we find using our algorithm. So the reason, however, why our mean average precision looks so good for this first attempt is that the test data set only had images that contained guns. So it didn't really take into account of a lot of possible false positives. So moving on to attempt number 2, or actually first, this was kind of the like real world performance of the first attempt. And as you can see, it can detect images of pistols, but it also detects an image of a person holding a phone as a pistol, which showed us that we had a kind of gaping hole in our strategy of not really taking account of possible false positives. So in our second attempt, we added in a roughly the equal number of images taken from the COCO data set, which is basically a massive data set of a lot of different images that have been labeled. And basically we took a random number or 2,500 random images from this data set that did not contain guns in them, basically to serve as more data for our model to know what wasn't a gun. And from this, you can see that our accuracy, mean average precision, went up to a max of like 96%. And this was, however, also still on a test data set that only contained guns. So it doesn't really provide us a full picture. And in real world performance, we saw that it definitely increased the accuracy in terms of the number of false positives much lower, but we still got, I guess, sort of unacceptable number of false positives. So in our third attempt, we used the previous weights generated from our second attempt to basically mine the COCO data set for images that our previous model thought were guns with 60% certainty or higher. And after we trained with those images instead of the previous random images of the COCO data set, basically targeting more on images that the model would be more likely to think as guns, along with the original 2,500 or 2,700-ish gun images that we trained on, you can see that we achieved much better results. And this was these 98% mean average precision was actually run on a data set of half gun images and half images that were mined as well from using the previous model.
Hey,
So
Jimmy, I
then,
have a quick question.
sure.
Regarding the mean average position metric, how does
Yeah.
it work when there's an image that does not have a gun in it, right? So like if you say there's a gun there and there's not, is it like a 0?
Yeah.
Okay.
Basically, it would be
And
counted
if
as a
there
0.
is and so okay, and then if there is not a gun and you say there's not a gun, then you count it as 100.
No,
Or do you just not count it at all?
yeah, you just don't count it all. Basically, if you don't draw a box and you don't need to draw a box, then that's just not. It's just fine.
Okay. Sure.
Yeah.
Sure. All right. Okay.
So then we have a quick demo video of attempt number 3, which was our latest attempt. And yes. So yeah, as you could tell in a couple frames, right, the guy was holding a handkerchief and that was detected as a gun. So obviously the false positive rate is still not ideal. And also this was run on a threshold of 50% or higher. So basically bounding boxes were drawn on basically images or whenever the algorithm detected 50% or higher certainty of there being a gun there. And as you can tell in the last couple frames, the model struggles a lot more when the gun is further away because there's less data. And yeah, as I'll get into our our current strategies for trying to improve this performance and moving forward. So basically now we're trying to increase our data set of real gun images. So basically images of guns in more varied positions, different depths, different orientations, because in real world in our tests, as you point guns in different orientations, the model will sometimes struggle in certain orientations. So we're working on increasing diversity of our data set. And then we're also increasing our data set to include hard negative images. So of images of commonly held objects like phones, pencils, all sorts of objects that people would normally be holding, just like the handkerchief or something like that, that could be confused as guns. We're also working on improving the labeling. So basically drawing bounding boxes on, I guess, the more defining characteristics of the gun, like the gun barrel instead of the hand. And that also, I'll get into that later as well. But basically, we're also experimenting with adding synthetic generated gun images because there are a lot of advantages with basically computer simulated gun images that are based off of 3D models, because you can control the textures on the guns, you can control the lighting, the angle, the different poses, the orientation of the hand to the gun. Basically, you control a lot of aspects and you can quickly generate a massive data set. So we're working to incorporate that as well in our training. And then moving forward, we also wanted to experiment with a certain technique that I found in a paper called random erasing data augmentation. And as you can see in the image, basically, you basically inside of the image, you randomly block out parts of the image with noise or black bars or white bars. And the idea behind this is that typically when training an object detection model, the model will tend to gravitate to certain features of the model or of the image. So basically if you had a facial recognition or a dog recognition model, it will tend to sometimes focus only on the dog's face. So then if the dog's face is covered, it'll fail to detect that there's dog in that picture. So instead, to mitigate this, you can randomly block off parts of the image so that the model cannot actually focus on only one specific part of the object you're trying to detect. So this will hopefully help us with, in case something is obscuring part of the gun in any images, or in the case where some part of the gun is not visible, or in some orientation where it's not easily seen by the camera. And we also wanted to experiment with other object detection algorithms that might be slower, but might have higher accuracy. So stuff like faster RCNN and a couple other algorithms that might help us improve accuracy. And then we can use this as sort of a second pass on detections from the previous model. So hopefully, if there's something that's not a gun, but we think is a gun, we can verify that quickly using another model. And that pretty much wraps up what we've been doing and how we want to move forward. So any questions?
Yeah, I have a couple questions.
Sure.
So I guess I've never implemented Yellow 4, so I can't. This is more of just a general question. But what kind of framework is it? Still based on Darknet?
Yeah, it is running off of Darknet.
So it's a single stage detector.
Yeah.
Okay. What was the clip that you showed us with all the guns? Was that running in real time, or did you kind of pass that? Like, I guess, can it run in real time?
So yeah.
Obviously, this wasn't in real time.
So this wasn't in real time, and I pre-rendered this to put it in the slide. But yeah, I think this was running on a Tesla T4 at it was greater than 30 frames per second. So it was definitely real time. And obviously with beefier GPUs, and if you adjust the resolution, input resolution, and some other parameters, you can get higher frame rates. But yeah, it's definitely in real time right now.
Okay. Okay. I guess kind of going into like how you plan to build this out in the future. So the reason like YOLO 4 was created by a different creator is because like the original creator kind of like stopped doing it because of privacy concerns. Yes. And like that's also a big thing going on with the whole like object detection thing. So I guess what kind of steps are you guys taking to also keep that in mind?
I mean, so I thought about this, and I mean that's part of the reason why I chose to move forward with this project, because unlike with like facial recognition, which can have like wide implications on privacy and like what is used for, like it could be used for identifying protesters or all sorts of things that really shouldn't be used for. I would argue that in almost, there really isn't any case where being able to detect the presence of a gun would be bad. like in a public area, right? If someone has a gun, you know, at least if you know that the gun is out there, you know,
it should be flagged, right?
Yeah. And also, we're not trying to focus on like holstered guns, and it's more of guns that are already drawn.
Sure.
So I guess that's something that also.
Sure. I mean, I agree with you. I just wanted to ask. Yeah. Okay. And finally, like the random erasing data augmentation technique that you talked about, does that have a significant impact on how it can run in real time?
This is more of a training technique. So it's just
augmenting
your data for training. Yeah.
Gotcha. Interesting. Okay. I guess again, in terms of how you guys are gonna like, what's the end product gonna be? Like, what are you guys imagining?
So after we, I guess, finalize our models and stuff like that, we'll probably just package it up into some sort of like one-click solution type of thing, maybe into like a Docker container or something that can be easily deployed. And yeah, something probably along the lines of accepting network streams of cameras. Or something like that, and then basically doing processing based off of that.
So like across surveillance cameras or something.
Yeah, something probably cloud-based.
Yeah.
Or at least something along those lines. Could be running locally on the local network as well, but yeah.
Sure. This is awesome. Good work, guys.
Yeah, thanks.
Do I guess Didi or Ansh have questions?
Yeah. First of all, great work. You thought of pretty much everything I could think of when I think of like a machine learning project, including how to augment your data and how to make it more accurate. But really quickly, earlier you mentioned that you weren't focusing on holstered guns. And I'm a little curious as to why that is, because I feel like if somebody pulls out a gun in a public setting, it's a little late for the camera to tell you that the gun is there, right? Like
the issue with holstered guns is
false positive.
Well, yeah, typically you're going to get a lot of false positives because, you know, usually a holstered gun can be behind like clothes, you know, it can be like on your belt, underneath the shirt. And it's just very difficult, I guess, to not have a high false positive rate, because then you're kind of looking at like imprints of like shirts, and like it just becomes very difficult at that
Problematic.
point. Yeah.
Yeah, I agree. I mean, it's hard to strike a balance between like what's most useful and like what's most feasible.
Yeah.
Something we've been asking, I guess, the other teams that have also presented. How did you guys end up dividing the work? Because this is a pretty big project. How are you guys staying organized and kind of dividing the work across y'all?
I guess you know, we all have different like amounts of times we can put in, but we just kind of assign stuff to people, and I mean, just get stuff done.
Okay.
Yeah.
I mean, fair enough.
Yeah.
Okay.
Yeah,
Didi, any questions?
looks really good. I feel like y'all asked all the questions that I had in mind.
Yeah.
Yeah. Do you have any parts that you want feedback on, like specifically?
Not right now. I connected with a mentor earlier, and if we have any questions, I'll be sure to ask.
Yeah.
I just thought
okay.
of another question.
Go for it.
Where do you see like the primary use case for this being? Like let's say you finish your model, you deploy it on AWS, anybody can check for guns with Docker on their own machine, right? So where do you want it to be used?
So it's a little difficult from a practical standpoint, because obviously like you would want to deploy this in like something like a school, right? But you can make an argument of like the practicality, because you could argue that, you know, you're adding cost, you know, GPU cost is not irrelevant to process constantly, and you know, you could argue that, you know, decreasing the response time by like a few seconds wouldn't really save any lives for the cost that it requires for the system. That's why we wanted to focus on like not having a very GPU intensive model. But I guess if someday you could pair this with some other sort of fast response system, so like in some hypothetical future where, I don't know, you could have like micro drones or something as like a fast response that could be like mass produced, and like basically if a gun's detected, right, and someone confirms that there's a gun in the school, right, you could quickly like deploy these drones to like take care of it or something like that. You know, that could be a use case. Obviously, there are a lot of implications with this sort of application, but the idea is at least that in any sort of public space like a bar or a movie theater, you could just use like conventional cameras and have the system running that could basically alert authorities with like basically more information and quicker. Because oftentimes, right, if you have like a large high school campus or something, right, and there's a report of a shooting, it takes police officers valuable time to know where exactly the shooter is. So if you have like cameras in each classroom, right, that can detect guns, and you can basically find and like notify authorities with much quicker speed.
I just thought of another potentially interesting application. There's a lot of interesting work being done with behavioral machine analysis. So kind of reading body language, like body temperature, and kind of just other subtle cues that tell. So, I mean, a lot of it is used for like gambling, basically, to tell if like poker players are cheating.
Mm-hmm.
But that's something that could be applied here, because someone just having a gun doesn't necessarily mean that the intention is harmful. But a lot of times when they do have that intention, it's visible through body cues.
Yeah.
So, and I don't think it's strictly machine learning either, which means it wouldn't hinder the the kind of real time processing that's needed for this.
Yeah, I mean, at the very least, like this can be deployed in basically areas where guns really shouldn't be out. Like,
True, that too.
yeah.
Fair. Like
Yeah.
schools.
Yeah,
There's
schools.
no excuse for anyone to
Yeah.
have a gun at school.
Yeah.
But yeah, I really like this project. I think it's timely, and I think it's going to be like very useful because it's already in a functioning state. So congratulations, guys.
Thanks.
Oh wait, here's a fun question. Sorry, I just thought of this one too. Like let's say your model gets to a state where it's being used automatically, kind of, right? So where you see a bunch of guns, and then maybe it like automatically reports to police and sends them the image so they can make a judgment call about whether or not to respond. Are you thinking about a way to exclude police officers from your model. So make it so that, because police officers generally should have guns. You could argue maybe not now,
Yeah.
but maybe exclude people who should have guns or similar weapons.
That's something I consider and I put in the design doc as like sort of a stretch goal to add basically object detection of like police officers in like uniforms, and basically as a additional functionality. But yeah, that's something definitely we could try to add in, but it all depends on time and stuff like that, and data. Data takes a lot of time to acquire.
Well, I hope like regardless of how much you guys finish during summer hacks, I hope you keep up with this project because I feel like it's very important.
Yeah.
But very well done. Great work.
Awesome.
Any final questions or thoughts from anybody here?
Go ahead and end the live stream, I guess.
Sweet. Okay. Well, thank you all for coming. As usual, feel free to message us with questions and have a good night.